Let's jump right into this explainer, shall we? Today we're looking at magnitude and direction, the fundamentals of vector engineering. This is, without a doubt, the invisible mathematical architecture that literally guides humanity to the stars, forming the absolute bedrock of modern mathematical modeling. So picture this. You're sitting in the driver's seat of your car right now. And suppose someone sitting next to you just says, "Hey, drive at 60 kilometers per hour. Is that enough info to actually get you to your destination? Well, no, not quite. Your immediate question is going to be, in which direction? Because speed all by itself, it's completely insufficient to get you where you need to go. Which brings us to section 1, the missing piece of motion. Because to fully describe how things move, we absolutely need a way to capture both how much and which way. Enter our mathematical hero for today, the vector. A vector elegantly solves this whole problem. It's simply a quantity that needs two essential properties to fully describe it: a magnitude, which tells us how large something is, and a direction. Engineers almost always represent this graphically as an arrow. The length of that arrow, that's your magnitude, and the way the arrowhead points dictates the path. So whether it's a 20 kilometer per hour wind blowing north or a 100 Newton force pushing eastward, the amount and the direction are permanently linked. It's a package deal. Moving on to section 2, scalars versus vectors. You know, to truly wrap our heads around vectors, we kind of have to look at the things that aren't vectors. There is just a stark contrast between how we measure different aspects of reality. On one side, we've got everyday scalars, like temperature, mass, time, and energy. These only need a magnitude. I mean, it doesn't make any physical sense to say, hey, it's 20 degrees Celsius to the left, right? But on the flip side, concepts like force, velocity, acceleration, and position, those are true vectors. They absolutely demand a spatial direction to make any sense in the real world. Section 3, forces, velocity, and position. The crucial takeaway here is how these quantities actually interact when things start moving and pushing out there in the physical world. Imagine person A pushes a heavy box with 100 newtons of force to the east. Now, person B steps in to help out, pushing with 50 newtons also to the east. Because both of these force vectors are acting in the exact same direction, they combine seamlessly. The total force on that box just became 150 newtons east. Simple enough, right? But wait, what if person B suddenly changes their mind and pushes 50 newtons west, directly against person A's 100 newtons east? Actually, they physically cancel each other out, leaving a net force of only 50 newtons east. This proves a really vital rule of engineering. Unlike ordinary scalar numbers, vectors cannot just be blindly added together. The direction completely dictates the math. And this brilliantly illustrates a super important distinction, the difference between speed and velocity. Speed is just a scalar asking how fast. Velocity, on the other hand, is a vector asking how fast and where to. Think about two aircraft traveling at 800 kilometers per hour. They have the exact same speed, but entirely different velocities if one is flying east and the other is flying west. Direction is absolutely critical data. Even physical position is a vector. It describes precisely where an object sits in space. Take a look at this position vector for a satellite. 7,000, 0, 0. That tells us the satellite is exactly 7,000 kilometers out along the x-axis with zero displacement on the y or z axes. These rigid position vectors are quite literally the absolute foundation of orbital dynamics and spacecraft navigation. Let's look at section 4, breaking down vector components. Because instead of just relying on an overall magnitude and a physical angle all the time, engineers need a systematic way to break these forces apart for complex computations. And that is exactly where component form comes in. By using components, a computer instantly knows how to process the movement. So a vector written as a matrix of 3 and 4 simply means moving 3 units in the x direction and 4 units in the y direction. Component form essentially takes a physical arrow in the real world and translates it into pure computable data. Then, from those components, we can easily find the total magnitude of the vector, which is 5 in this case, using the classic Pythagorean theorem you probably remember from high school math. 3 squared plus 4 squared equals 5 squared. It's an elegantly simple mathematical foundation that empowers engineers to scale up to incredibly complex real-world physics. Section 5, navigating with coordinate systems. Because vectors don't just float around in a void, they always exist relative to a coordinate system, essentially requiring a structured map to exist on. Engineers actually have to tailor these maps for different disciplines. For basic mechanics and robotics, standard Cartesian coordinates work perfectly. Radar systems, they rely on polar coordinates. But in space engineering, it gets intensely complex. You've got Earth-centered Earth-fixed frames for GNSS systems and Earth-centered inertial frames, which are fixed relative to the distant stars for tracking orbit dynamics. Translating vectors seamlessly between these various coordinate systems is basically one of the most vital tasks in all of aerospace engineering.
Which brings us to Section 6, the backbone of engineering. This takes us from the driver's seat all the way into the cosmos, showing exactly why this mathematical bedrock actually matters to our lives.
The reality is, vectors are the exclusive mathematical language for describing motion, forces, orientation, and position. Without them, modern engineering would just collapse. The GPS coordinating your phone's maps, the spacecraft in orbit, commercial aircraft, industrial robotics, and the autonomous vehicles being developed today, every single one of them relies entirely on vector mathematics to function safely and accurately. It's practically magic, but it's just really good math.
Once you truly grasp this elegantly simple concept of magnitude and direction, you unlock the door to the most advanced engineering concepts humanity has ever developed. Vectors are your gateway to understanding matrices, complex coordinate transformations, state space models, and even Kalman filters. Literally everything builds on the arrow.
I'll leave you with this final thought to ponder from our source material. A number tells you how much. A vector tells you how much and in which direction. In engineering, direction often matters just as much as magnitude. So I'll ask you, in a universe that is constantly in motion, is knowing how much ever really enough without knowing where to?